Welcome to solverfy.
So to find the image formed by the first lens, we're going to use, of course, equation 23-8. Equation 23-8 in general says that 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. Therefore, in general, the distance to the image is equal to the distance to the object times the focal length divided by the distance to the object minus the focal length. So in our case, the focal length of both lenses is the same. So I said f1 is equal to f2 is equal to 25 centimeters. And the distance to the object of the first lens is equal to 35 centimeters. And we also know that there's 16.5 centimeters in between as a separation of the two lenses. So the distance to the image produced by the first lens, we'll call that di1, is going to be equal to the distance to the object of the first lens, d01, times the focal length divided by the distance to the object of the first lens minus the focal length. And this is, of course, f1 in this case, although it doesn't really matter since they're the same for both. But plugging those values into this expression, we find that this is equal to 87.5 centimeters. Okay, so this image is going to be used as the object for the second lens. Because it's beyond the second lens, right? Because the distance between the first lens and the second lens is 16.5 centimeters. So because it's beyond that distance, it's going to have a negative object distance, right? So the distance to the second object, we'll start a new page for this, we call D02 is going to be equal to 16.5 minus what we just found, 87.5. And this comes out to be equal to, of course, both these have units of centimeters, so let's go ahead and explicitly write that. We'll just pull the centimeters out. So these are both units of centimeters. So this gives us negative 71 centimeters. So using this, we can now find the distance to the image of the second lens using our formula. So this is going to be the distance to the object of the second lens times the focal length of the second lens divided by the distance to the object of the second lens minus the focal length of the second lens. So plugging those values into this expression, we find that this comes out to equal 18.5 centimeters. And this is going to be past the second lens, right? 18.5 centimeters on the other side of the second lens, past it. So we can go ahead and write that here. So that's explicitly stated. We'll just say past the second lens and box that in as part of the solution to the question. That was one of the things we were asked to find. Okay, now the second thing that we were asked to find is something we can use the total magnification for, right? Because we're asked to find the total magnification, we can use the fact that, and we'll start a new page for this, the total magnification, we'll just call this M, is equal to the magnification of the first multiplied by the magnification of the second. Okay, well, by definition of magnification, this is going to be equal to minus the distance to the image of the first lens divided by the distance to the object of the first lens multiplied by, And now we have M2 magnification. This is going to be minus distance to the image. Let's rewrite that D, make it a little nicer. Distance to the image of the second lens divided by the distance to the object of the second lens. Okay, so we know all these values. Plugging this into the expression, we find that this is equal to negative 0.651. And since this is negative, this is inverted. So we'll just type inverted. We'll box that in as the next part of the solution to our question.